This is problem 16.6. It's on page 1139. A 2,000 kilogram truck is being used to lift a 400 kilogram boulder B that is on a 50 kilogram pallet A. Knowing the acceleration of the rear wheel drive truck is 1 meter per second squared, determine A, the reaction at each of the front wheels, and B, the force between the boulder and the pallet. I'll refer you to the figure in the text for dimensions. But what I did is I began by noting the mass of the truck, 2,000 kilograms, mass of the boulder B, 400 kilograms, mass of pallet P, 50 kilograms, and then also noting that we want to find, put this down here, well, I guess we'll put it up here, want to find, let's see, the normal force at the front tires on each tire, and we wanted to find the force between the boulder and the pallet. Okay? I started off with a free body diagram of just the truck. Here's the truck. It's rear wheel drive. There must be normal force at the front and rear wheels. And therefore, since it's rear wheel drive, the friction force is at the rear, propelling the truck forward. The center of gravity of the truck is at G here. And I just went ahead and drew the weight of the truck here. And then there's tension acting on the back of the truck. Okay, and those are all the forces. Now, I drew this because I decided to put my free body diagram and kinetic diagram together. And write mass, in fact, you know what, let's put that in a different color to differentiate the dynamic forces from the real forces. So there's a mass times acceleration in the y direction, as well as a mass times acceleration in the x direction, and then finally an I alpha to be complete in our kinetic diagram. However, we set up our typical xy coordinate system. However, you know that the truck does not accelerate in the y direction, and it does not accelerate angularly. So we're going to just cross off the dynamic force in that dynamic moment. And then from that, we can start to analyze it. Now, one thing we need to note is kinematics. Let me hold off on the kinematics for a moment. So for the truck, save some space here for another free body diagram in a moment. Well, you know what? Actually, let's put that free body diagram with the sum of force, sum of moment equations. Anyway, so for the truck, if we sum moments about R, taking counterclockwise as positive, where R is this point. Why did I choose that point? Well, I don't care about the normal force of A, and I don't care about the friction force. I don't even want to bother computing them. So if I sum moments about that point, calling it R, well then those two forces will go away. They won't appear in my equations. So let's see, what do we have? Well, we've got tension acting to cause a negative moment. So negative T times 0.6 meters, right? Because the height from the ground up to that toe point is 0.6 meters. Plus the weight of the truck, notice it's causing a positive moment about R, and the moment R between the rear wheels and the weight is 2 meters. And then, since the force on the front wheels of the truck, I want each one of these, really let's do it this way. There's two of them, right? Because there's two wheels. So that I didn't forget later, I wrote minus 2 in F, the force on the front wheels, times its moment arm, which from here to here is 3.4 meters. So 2, so that I'm taking into account when I calculate NF, it's just the force of one wheel, which is what they want. So that way I didn't forget to do it. Times 3.4 meters then. I'm out of space, so let me break the line and write equals on the right-hand side. Well, we've always got I alpha, but wait a second, alpha is 0. We've got the moment of A in the y direction times the moment arm. Well, that causes a negative moment, so minus MAY times its moment arm of 2 meters. But wait a second, that's 0 as well, isn't it? And then for x, well, MAX has a moment arm. And notice that MAX, the center of gravity, is above the toe point. In fact, it's 1 meter high. Very simple dimension. And so we'd write negative MAX multiplied by 1 meter. Now, if I drop the units and just start plugging in numbers, we have negative t times 0.6. All the units should be consistent because the tension should be like the weight in newtons. That'll give me NF in newtons. The mass will be in kilograms, acceleration in meters per second squared, and all my length dimensions in meters. Well, then everything's consistent. I don't have to worry about it. Plus the weight of the truck, which is not 2,000 kilograms. It's 2,000 times 9.81 meters per second squared. Now we've got newtons in that product. Times 2 from there, minus, I just combine those two, 6.8 in F equals, and on the right-hand side, we just have negative MAX. Now, one thing I forgot to mention that I read is that the truck is accelerating to the left at 1 meter per second squared. That means the acceleration of the truck in the x direction is negative 1 meter per second squared. So on the right-hand side, calculating that right-hand side is pretty trivial because we just get the mass 2,000, the negative signs cancel. So 2,000 is the number on the right-hand side. Okay. So what does this do? It gives us a relationship between the pulling tension in the rope and the front tire normal force. In fact, if we continue and write negative 0.6 T plus multiply all this out, I got 39,240 for that product, minus 6.8 in F equals 2,000. Let's see, wait a second. I may have made a mistake along the way because when I wrote it down, I have this is negative, this is positive, this is negative, and I have the right side as negative. Why did I do that? MAX, yeah, that's right. I may have a mistake in my solution. This negative sign comes from the moment. And this negative sign, there's my problem. Yeah. So the acceleration is actually in that direction, so we should get positive. Actually, that's correct. I'm not sure what's going wrong. Let me continue, and I'm going to put a negative sign in here. You'll have to investigate and figure out where that comes from, but let me put the negative in here, and I may be wrong, but the answer I got made sense to me, so I'm not sure. Anyway, so if we have all of that, let's see, actually when I rearranged it, yeah, no, it is positive. Yeah, I'm not reading my sheet right, never mind. So it's positive, and that one, when I take this to the other side, it's, we get negative 0.6 T minus 6.8 in F. I just have to read my sheet right, and then we're okay. 2,000 minus 39,240, and that is negative 37,240. There we go. And so basically my equation ends up being 0.6 T plus 6.8 in F equals 37,240. Okay, I call this equation 1 because it just relates T to NF. Now a little bit of kinematics if you think about it. We've got a boulder and pallet to consider. So actually let's take care of that next. Boulder and pallet. And for this, I'm going to make a free body diagram of the pulley with rope tension acting on it and the pallet and boulder. Now obviously the weight of the pallet plus the weight of the boulder acts downward while the tension acts upward. If we sum forces in the vertical direction, we get 2 times the tension minus the weight of the pallet minus the weight of the boulder. And I don't even need a kinetic diagram here because it's so trivial. It would just be MAY up, where M would be the mass of the pallet and boulder. So I just wrote on the right-hand side mass times acceleration, mass of pallet, plus mass of boulder, times the acceleration in the vertical direction. Now, the acceleration of the pallet and boulder is related to the acceleration of the truck. If it's a 2-to-1 ratio, then you realize, well, as the truck moves, say 1 foot forward, the pallet will only move a half foot up. So what that means is that let's see, some kinematics here. I guess I'll carve out this space for kinematics. They're pretty easy. The velocity of the truck is 2 times the velocity of the pallet boulder system, right? So that means that the acceleration of the truck is twice the acceleration of the pallet. Now we realize the pallet has to accelerate in the positive y direction if the truck is accelerating to the left because of the way the pulleys are configured. But the point is that this acceleration in the y direction is just 1/2 meter per second squared. That's the point of the discussion. Okay? And so if we take this and rearrange it just a little bit, we can say that 2 times the tension, let's take these to the other side, equals the weight of the pallet plus the weight of the boulder plus the mass of the pallet plus the mass of the boulder times the acceleration in y direction. We'll plug that in just a moment. Now notice that the weight of the pallet and boulder is equal to the mass of the pallet plus the mass of the boulder times the acceleration of gravity. So if we combine that with the second term, it would look like this: mass of pallet plus mass of boulder times G plus AY. Okay? So the effective weight that the rope is pulling against is a little bit more than the actual weight. There's some dynamic weight because of the acceleration in the vertical direction. Okay, so basically the tension then would be this thing over 2, so let's just write it that way. The sum of the mass of the pallet and boulder is just 450 kilograms. We've got to divide by 2 to get that factor on the other side, and then multiply by G, 9.81 meters per second squared, plus 1/2 meter per second squared of acceleration, see. And so the tension in the ropes comes out to, let's see, 2,319.75 newtons. So there's the tension of the ropes. Now that we've got that, we can go back up to equation 1 here and solve for the force on one front tire. Well, that would simply be 37,240, which is on the right, minus 0.6 t, all divided by 6.8. So if we plug that in, plug in t equals what we just found, 2319.75 newtons. Notice all the units are consistent, and we end up with about 5,271.79 newtons of force on the front wheel. So there's the force on one front wheel. But that's not all we were asked to find. We were asked to find the force between the boulder and pallet. Okay, so we'll take care of that next. Let's take another free body diagram. How about a free body diagram of just the boulder? Well, with just the boulder, we'd have what? Force from the pallet acting up and weight of the boulder acting downward. So if we sum forces in the vertical direction on this free body, we'd have force on pallet, or force from pallet minus weight of boulder equals mass of boulder times acceleration in y direction. Because notice the boulder is accelerating at the same rate as the pallet. Therefore, the force from the pallet has to support both the weight of the boulder and the dynamic force of the boulder, you see? And so that would be the mass of the boulder multiplied by G plus AY. And so the mass of the boulder, 400 kilograms, times 9.81 meters per second squared plus the 1/2 meter per second squared will give us the force from the pallet, and that comes out to a force of 4,124 newtons. And there's the force from the pallet on the boulder.